Hello all, I'm back with another video, and this is another past paper walkthrough paper, and it's the first one on Unit 3, okay? So this is the first time we were going over a Unit 3 paper, and it's from the most recent exams taken in October 2025, and for whatever reason, there is also a Unit 3A test, which is different from this one. But okay, let's get done with this one first and see what to do with the other one in the near future. So just grabbing my calculator in case I need it. So let's go. Question 1. A student used the micrometer screw gauge to measure the diameter D of the glass tube shown. Okay, and we have a glass tube. The walls of the glass tube are very thin. Identify a health and safety issue associated with this measurement and how it may be dealt with. Okay. So the problem is that it's a glass tube, right? So if we use a screw gauge, as we tighten the screw gauge, we might actually break the glass and it might get into our eyes or hands or whatever. So it's dangerous. Okay, so you need to use protective glasses and gloves at the same time. So let's write that down. So the screw gauge, okay, might break the glass. Oops. Might break the glass. Hence we need both protective gloves and glasses. Okay, in case the shutter glass goes into our eyes. Okay. B. The student made measurements to determine a mean value for D. He measured D at different orientations along the glass tube. Explain another technique he should use to reduce error when measuring D with a micrometer screw gauge. So he has to ensure that the zero error of the micrometer is accounted for to avoid systematic errors. Okay. Part C now. The student recorded the following measurements, and we see we have 5 measurements. Okay. Calculate the mean value of D. So this is fairly simple. We just add the 5 values and divide them by the number of values, which is 5, right? So we have 3.19 plus 3.22 plus 3.19 again plus 3.21 plus 3.2 over 5 yields 3.2 millimeters. Right. Determine the percentage uncertainty in the mean value of D. Okay, so first of all, we need to find the absolute uncertainty. And whenever we have a set of measurements, the absolute uncertainty, in case we have more than one measurement, okay, in this case, we have 5 measurements. So to find the absolute uncertainty, we need to find the half range. Okay, so let's start with that. So absolute uncertainty in D, absolute uncertainty is with a U, okay, in D is equal to half range right, to the half range, I'm sorry. And the range is determined by finding the two extreme values, the highest and the lowest. Okay, so the highest is 3.22, the lowest is 3.19, right? So 3.22 minus 3.19 over 2 yields 0.02. I'm running out of space today. I don't know what's wrong. Maybe it's because I'm filming this a little bit late in the night. So 0.02 millimeters, okay? And then the percentage uncertainty in the mean value, okay, is given by the absolute uncertainty over d, the mean value, okay? Actually, sometimes you can write the mean value as d with that hat on top, but that's fine. So 0.0, oops, and we need to multiply that by 100 times 100%. So let me raise this. So 0.02 over 3.2 times 100% yields 0.47%. Okay. And just like that, problem 1 is gone. And problem 1 is 8 marks. So again, I said probably in all my past paper videos, but 8 marks usually means that you have to spend around 8 minutes on this problem. And I cannot recall how much time you have on unit 3. Let me see. You have 1 hour and 20 minutes, okay? So yeah, 8 minutes. Unit 3 and unit 6 are usually unit 3 and unit 6 have 4 questions. So yeah, 8 minutes is good for problem 1. Let's move on. If it takes 10 minutes, it's fine. I mean, don't panic. So question 2, a student investigated the diffraction of microwaves using the apparatus shown. And we have a microwave transmitter, a gap, and metal plates. Okay, cool. And we have a microwave receiver. Okay. The student placed the microwave receiver opposite the center of the middle metal plate. The student, okay, question A, the student moved the microwave receiver towards point P. The microwave receiver detected a series of maximum and minimum values of intensity. Explain why there are positions of minimum intensity. So, so there is a path difference pretty much, okay? I mean, if you have a wave that comes from this gap, okay, and a wave that comes from this gap, as you can see, they superimpose there, and in the middle you have a maximum, okay? But then the path difference has to be a multiple of lambda or lambda over 2 for constructive and destructive interference, etc. Okay, so let's write that down because they don't require us to write any math, so we will just write it in words. So the waves, okay, travel through the two slits. So they actually ask for minimum intensity, okay? So the waves travel through the two slits and superimpose. Okay, minima are points where the path difference is equal to 2n plus 1 times lambda over 2, where n is 0, 1, 2, etc. Okay. Part 2. The student located the first position where the intensity was a minimum. The student used vernier calipers to measure the distance x from the initial position to the position of this minimum. identified two possible sources of uncertainty in the measurement of D. So first of all, it is difficult to locate the center of the receiver. Okay, and it's also hard to ensure the calibers are parallel to the plates. Okay, so that's a possible answer, I guess, because you will have to put the calibers right here, I guess. Okay, let me erase. So you will have to somehow put the calibers right there and then kind of try to adjust them and then move it across, parallel to the plate. So it's really hard to keep those calibers parallel to the plates, also figure out where the center of the receiver is and so on. Okay, so it requires delicacy in the handlement of this instrument, I guess. So let's go to part B. The students suggested that the wavelength lambda of the microwaves is given by that expression over there, lambda equal to 2 times x times lowercase d over uppercase d. And then they say where d is the distance between the centers of the gaps in the metal plates, d is the perpendicular distance between the metal plates and the initial position of the receiver. Calculate the frequency of the microwaves. Okay, we can actually calculate the wavelength first. Okay, so lambda is simply 2. I'm just copying down numbers. X is 17.84 centimeters, so I need to convert it to meters by multiplying with 10 to the minus 2. And then D is 4.09 centimeters, so again times 10 to the minus 2. And this is meters squared because we are multiplying two lengths, right? And then we divide with a length 0.502 also meters. So meters cancel, and we find the wavelength as equal to 0.029 meters, okay? And then we know that for electromagnetic waves, they propagate with the speed of light, so C is lambda times the frequency, therefore F, the frequency, is C over lambda, so 3 times 10 to the 8 over 0.029, and this is meters per second, and this is meters, so meters cancel, and we find 10.32 megahertz. Beautiful. Okay, the student increased the value of D, which is again the perpendicular distance between the metal plates and the initial position of the receiver. Okay, explain how increasing D reduces the percentage uncertainty in X. So X again is what is X? Okay, the wait, where is X mesh? Okay, X is the distance from the initial position to the position of a minimum. Okay, so what's going to happen if D increases? Okay, the distance between the minima will increase. okay? And you can think about this if you ever saw a laser experiment. If you pull the screen further away from the laser and the position of usually they use grating or a double slit or something like that. As you move it back, you will see that the distance between the maxima increases, okay? And this is because the angular distance is larger, okay? So yeah, so if d increases, the distance between the minima will increase. So the distance x between the minima, okay? So let me pull this there, okay? The distance x between the minima will increase. The absolute uncertainty in x remains the same, right? Because the absolute uncertainty for one measurement is related to half the smallest deviation of the instrument you're using, okay? So you're going to be using the same instrument in both cases. Therefore, the absolute uncertainty remains the same. But the percentage uncertainty in x is equal to the absolute uncertainty in x over x times 100%. So since x increases, the percentage uncertainty in x decreases, and that's the answer. Okay. So we are also done with question 2. Beautiful. Let's move on to question number 3. A strain gauge is a sensor made from metal foil fixed to a plastic sheet as shown, okay? Bending the plastic sheet changes the dimensions of the metal foil. This changes the resistance of the metal foil. A student connected the strain gauge into the circuit shown below, okay? The student switched on the power supply and the voltmeter displayed the following reading. Determine the percentage uncertainty in this reading. Again, we just talked about the absolute uncertainty. So the smallest deviation of this instrument is 0.1 millivolts, right? So the absolute uncertainty, so the percentage uncertainty is equal to the absolute uncertainty over, let's call it in the voltage, right? Over the voltage times 100%. So the absolute uncertainty here is 0.05, right? Over the actual value, which is 16.2 times 100%. And this gives you 2 marks. So 0.31% is the answer. Small. Now, let's go to part B. The student adjusted the variable resistor in the circuit so that the reading on the voltmeter was 0 millivolts. He attached the strain gauge to a wooden meter rule. Okay, there it is. He clamped the meter rule to hang over the edge of a bench as shown. Okay. The reading on the voltmeter increased. The student adjusted the variable resistor again so that the reading on the voltmeter was 0 millivolts. Explain the reason for this adjustment. So the weight of the ruler causes strain, okay, which if not eliminated causes systematic errors. And that's the answer. So you have to get rid of that so you don't have a systematic error. Part 2. The student attached a 500 gram mass to the meter rule at a distance L from the center of the strain gauge. The strain epsilon can be calculated using the formula shown there, where W is the weight of the 500 gram mass, E, capital E, is the Young modulus of the wood, B is the width of the meter rule, T is the thickness of the meter rule. show that strain is 1.5 times 10 to the negative 3, and they give us the Young's modulus, the length, the width, and the thickness. All right, so this is a straightforward application. So let's plug in the numbers. Epsilon is 6 times the weight, which is 500 grams, so 0.5 kilograms times G, which is 9.81. So we already have, again, my strategy is to put all the numbers when I'm performing a numerical calculation, I put all the numbers to the left and all the units to the right. So the units here so far are kilograms and then meters per second squared for G. Then we have the length 0.513, and this is meters, so we can write meter squared. And then we have the Young's modulus, which is 11.9 gigapascals, which is times 10 to the 9 pascals. And 1 pascal is 1 Newton over meters squared. Okay. And actually, I'm going to erase this meter squared, and I'm going to write it as meters. You will see why in a moment. Okay. Then B is in millimeters, so let's write it as 0.0253, also meters. Okay. And then we have T squared, so 5.8. I run out of space. Let me pull this to the right a little bit. Okay, over there is good. And then 5.8 times 10 to the negative 3 squared, and then we have meters squared. Okay, so this guy over here, kilograms times meters over second squared, makes 1 Newton, right? Because F is ma. Therefore, the units for F are the units for mass times the units for acceleration. So 1 Newton is 1 kilogram times meters per second squared. Okay, so newtons cancel. And then we also have another beautiful cancellation. So meters and meters, meter squares with meter squares, and strain is dimensionless as it should. Okay, so if you plug in the numbers, you actually find 1.49 times 10 to the negative 3, which is about 1.5 times 10 to the negative 3. Okay. Question 3, the student added more masses to the meter rule. For each mass, he recorded the reading V on the voltmeter and determined the corresponding value of epsilon, of strain, right? The student recorded the following data to plot a graph of epsilon against V. Criticize the recording of the data. Okay, so these types of questions, they usually they don't ask you about the physics of the problem usually. Okay, they usually ask you about the nature of the data themselves. So for example, here we have inconsistencies in the number of significant figures used, right? So that's the first observation. Then we don't have repeats. For example, when we say repeats, we mean you can measure for 500 grams twice, record the strain, and then take the average. Then we have this weird situation here where the voltage, we increase the mass and the voltage decreases, and then we increase the mass again and the voltage increases. So that's inconsistent again. So these are all things you can write. So, and also, of course, we just have 3 data points. That's not enough. So not enough data points. So just 3 are used here. Inconsistent significant figures, sig figs. I'm gonna write it like that. V decreases and then increases as mass increases, which is a bit crazy, and then there are no repeats. So these are all valid points to include. Okay, so this problem awards 3 marks. Usually if you include 3 out of these 4, it's gonna be fine, but if you include more, that's not an issue. Okay. Now, question C. Engineers use strain gauges to monitor the forces exerted on aeroplane wings. Suggest 2 reasons why engineers need to monitor these forces. So I guess in an aeroplane, we don't want the wings to bend too much, so no excessive bending. Okay. That's one. They can, I guess they use this to check the strength of the wings. So checking the strength of the wings. And a third point is that they probably measure this to test various materials. So testing various materials. All right. So we are also done with question 3, and we are left with the last question, question 4. So a student determined the value for the acceleration of free fall g using the apparatus shown. So there are some slotted masses, a ramp, and a cylinder. The student released the cylinder at a distance s from the bottom edge of the ramp. She measured the time t for the cylinder to travel the distance s. Describe an accurate method to determine t, the time, using a stopwatch. So I guess the first thing to make sure is to keep h and s constant, and record t for 5 times. Okay, so you have enough data. You can add a marker at the end of the ramp. Okay, for accurate timing. I mean, you will have a visual clue about when the cylinder passed through the end, so you stop the stopwatch. And another thing you can do is to start the stopwatch as soon as the cylinder starts moving. Okay, part 2. The students suggested that adding a light gate near the top of the ramp and a light gate near the bottom of the ramp would improve the measurement of t. Describe advantages and disadvantages of using light gates to measure t. Okay, so first of all, light gates work instantaneously. Okay, the uncertainty in the measurement of t is reduced. What else can we write? So, and also the light gate gets triggered immediately after the cylinder starts rolling. Okay. Part B. In this investigation, the relationship between T and H is given by that formula over there, where R is a constant. Explain how a graph of 1 over T squared against H can be used to determine the value of G. So I'm going to do this right there. So this has the form of Y equals mx plus C. Okay, with, so m is the gradient of the curve of 1 over T squared versus H, right? And is equal to G over 3s squared, right? So G is going to be 3s squared times the gradient of the curve. And that's the answer. And now we have to do a calculation, I guess. So the student varied the number of slotted masses to adjust H. She determined corresponding values of T and recorded the following results. Complete the table with corresponding values of 1 over T squared. Okay, that's part 2. Let's do it. So 1 over T squared is in seconds to the minus 2. So the first value is 0.22. And then 0.20, 0.14, 0.09, and 0.05. I'm bad in copying, I guess. 0.05. Okay. Part 3. Plot a graph of 1 over T squared on the y-axis against H on the x-axis on the grid opposite. Okay. So at some point I might cut the video, I guess, but let's start with the axis. So this is the y-axis. So we will have 1 over T squared here, which is measured in seconds to minus 2. And our x-axis will be the height. So this is the height in meters. Okay, so we can make these squares, the big squares, 0.05, 0.1, 0.15, 0.20, and 0.25. All right. And then we can make these big boxes 0.02, 0.04, 0.06, and 0.08. Okay. So first point, 0.066 and 0.22. Okay. Okay, and now is the time. Let me see, 0.066. So this is 0.07, I guess. So this is 62, 64, 66. Okay. And now I'm thinking internally. I'm sorry, guys. I hope this video makes sense. So 0.22 is gonna be this thing over there. So let me think. 62, 64, 60. So this is the first point. Okay. Okay, I'm back. I'm gonna draw the line of best fit. So this looks good. Okay. And let's move on. Okay, this is the graph, I guess. Okay, as you can see, if you extend it, it goes to the negative of the y-axis as is shown by that constant over there. Okay. Determine a value of G from the graph. Okay, so the gradient, and now I'm going to use points from here. So I'm going to use the extreme point, so these pairs here. Okay, so 0.22 minus 0.05 over 0.066 minus 0.022. By the way, you can use any points you want. So this is 3.86. And now G, as we said, is 3s squared times the gradient. So it's 3 times 0.9 squared times 3.86. which yields 9.39 meters per second squared. Okay, a little bit off, but not horrible. Okay. Final question, the student determined the value of G as 9.56 meters per second squared with a percentage uncertainty of 4%. Deduce whether the student's value of G is consistent with the accepted value. Okay, so multiplying G times the percentage uncertainty in G, okay, gives us the absolute uncertainty in G. Okay, so the absolute uncertainty in G is 9.56 times 4%, which yields 0.38 meters per second square. So G is in reality 9.56 plus or minus 0.38 meters per second square. The upper bound G max is 9.56 plus 0.38, which is equal to 9.94 meters per second squared, which is within, sorry, so that's the upper bound, okay? So 9.81 meters per second squared, which is the accepted value, okay, is within the calculated range. Hence, the student is accurate. Okay, and this was Unit 3 from the most recent exam period of October 2025. I hope you guys find these videos useful. I'm happy to see the channel growing a little bit. So yes, let's keep it up. Please like and subscribe, and recommend these videos to your friends who need them or something like that. Help me grow this channel. Hopefully make it, I don't know, a permanent job or something. But anyway, thanks for those of you who provide comments or ask questions or like the videos or watch the videos and so on. So I'm gonna see you in the next one. Bye.